All right, we have Chapter 6, Discrete Probability Distributions. It has two sections. The first section is just getting more familiar with what a discrete random variable is. And the second section is a very long section about the binomial probability distribution. So we'll be spending a lot of time discussing what binomial means and how the probability distribution works. So section 6.1. We distinguish between discrete and continuous random variables, talk about what a discrete probability distribution looks like, compute and interpret the mean of a discrete random variable, and also the standard deviation of a discrete random variable. All right, so a random variable is a numerical measure of the outcome of a probability experiment. So it's a random variable. It's a numerical measure of the outcome of a probability experiment. Its value is determined by chance. So by chance, like flipping a coin, heads or tails, rolling a die, all the different sides, playing cards, all random variables. We use capital letters to denote a random variable. It's generally the capital letter X. So X represents the different outcomes of random variables. If I flip a coin, it should be I. If I flip a coin twice and count the number of heads, what are the possible values of the random variable X? So if I flip a coin twice, I could get 0 heads. I could get tails both times. I could get 1 heads, 1 tails, or I could get 2 heads, no tails. So my different random variables are 0, 1, or 2. Those are the numerical values that I can get. If I flip a coin 5 times and count the number of heads, what are all the possible values? Well, if I flip it 5 times, I could get 0 heads, or 1, or 2, or 3, or 4, or I could get 5. I couldn't get 6 or 7 or anything else because I'm only flipping it 5 times. And don't forget that you could have 0 successes. You could have 0 outcomes of what you're counting. So if we're counting the number of heads, it's always possible to get 0 heads. So those are distributions of all the different possible number of heads. That's what we're counting. So a different example, if I measure the time between cars at a certain intersection. So let's say I have a stopwatch or I'm on my phone with a timer and I'm timing how long goes between cars at a certain intersection. What are all the possible values for X? This time I can't just list them out 0, 1, or 2 because there could be any number of times greater than 0. If I'm starting and stopping a stopwatch, all kinds of different numbers could appear. So there's infinitely many decimals, infinitely many numbers, and the way we represent that is that X, our random variable, can be any number greater than 0. There has to be at least more than 0 seconds between cars at an intersection, but the time could be really long, really short, and all kinds of possibilities in between. So this time we write it a little bit different. X can just be greater than 0. So there's two types of random variables. There's discrete and continuous, just like in chapter 1. So a discrete random variable can be counted and has a finite number of outcomes. So we count how many of whatever we're talking about. That's what chapter 6 is about. Then we talk about continuous random variables that have infinitely many values and are usually generated from measuring how long, how much weight, height, volume, and all of that will be covered in chapter 7. So discrete is what we're discussing in chapter 6, and then continuous in chapter 7. So here's some examples. We need to decide if they're discrete or continuous, and then try to think of the possible values for the random variable X. So if I want the number of students in the class who got an A on the exam, on whichever exam I'm looking at, the number of students, that is a count. If we're counting, that's discrete. And X could be 0 or 1 or 2, so no one got an A, one person got an A, 2 people got an A, 3 people got an A, all the way up to the class size. which varies. Usually it's around 30. So whatever the class size is, that would be the maximum value. I can't have more A's than I have students in the class, so there's a limit on it. B, the speed of the next car that passes through the intersection. Speed is a measurement, and so it would be a continuous random variable, and X could be any number greater than 0, because if it's going through the intersection, it must be going more than 0 miles per hour. C, the number of light bulbs that burn out in the building with 20 light bulbs. So there's 20 total light bulbs. We're counting the number that burn out. So that is a count. If it's a count, it's discrete. And X could be 0, which means no lights burn out. 1, 2, 3, all the way up to 20. It has, again, that limit of 20. And then D, the time it takes for a light bulb to burn out. So if I had a stopwatch or a timer running, time, again, is a measurement. If it's a measurement, it's continuous. And X could be any number greater than 0. Some students argue it could be equal to 0 if you turn the light on and it instantly burns out. So it's not that big of a deal which way you write that, as long as you know that it can take on an infinite number of values greater than 0. So that's the difference between a discrete random variable and a continuous random variable. Again, we're just focusing on discrete for Chapter 6. So a discrete probability distribution is all the possible values of X, all the different outcomes it can have, and the probability of each one occurring. Very similar to Chapter 5. So just like other probability distributions, the probabilities must all be 0 or larger, at least 0, and the sum of the probabilities must equal 1. So if I look at chart A, here's all my different outcomes for X, here's the probability of each outcome, and this one does not make any sense because it's negative. So this is not a valid model. Again, it's just like Chapter 5. B, here's all my probabilities. They're all between 0 and 1. Let's see if they add up to 1. And they definitely do not, unless I mistyped. Nope. So the sum is not equal to 1, so it's not a valid probability model. And then part C, or chart C, looks like they're all valid between 0 and 1. Let's see if they add up to 1. And they do. So the sum is equal to 1. All of these values are positive, and none of them are greater than 1. So that's a valid model. So again, it's just like Chapter 5. Nothing can be negative, nothing can be greater than 1, and the sum needs to be exactly 1. So now we're going to look at the mean, or the average, of a discrete random variable. To do this, we multiply the random variable, or the different outcomes, with the probability of it occurring, which we call P of X, probability of X occurring. And then we take the sum of all of those values. So this data I pulled represents a high school football player's percentage of successful field goals out of 5 attempts. So we could have 0 successes, 1, 2, 3, 4, or 5 successes. And here's the probability of his past success. So I'm going to take each X value and I'm going to multiply it by its probability. So if I take 0 times 0.3, that gives me 0. So I'm doing X times P of X. And then 1 times 0.16, which is 0.16. 2 times 0.02 is 0.04. 3 times 0.23. 4 times 0.14. And 5 times 0.15. So I'm taking each outcome and multiplying it by the probability that it occurs. And then I'm going to take the sum of that. So I'm going to add all those up. 0 plus 0.16 plus 0.04 plus 0.69 plus 0.56 plus 0.75. I add them all up, and I get 2.2. That is the sum of each X value times its probability. That formula is on your chart. Under Chapter 6, you'll see the mean, or what we call expected value. I'll explain that in a second. The sum of each x times its probability. So that is on your formula chart. You don't have to memorize that. So this is how we get the average, a little different. We don't add them all up and divide by 6. It's a little different because each one has a different probability. They're not equally weighted. So because of it, they're unique probabilities, we have to do this a little bit differently. So that's the formula. So we take it and we call it, this is just in the book, it just explains it. We call this an expected value, or E of x. An expected value. So it's a little bit different. It's still the average, it's still the mean, it's just calculated differently, and we think about it a little bit differently for these random variables. So we use the mean of a discrete random variable to represent what we call the expected value for this random chance event. It's what we expect to happen. So for this example, the mean would be the expected value for the field goals made out of 5 attempts. Another way to say that is an average of 2.2 out of 5 attempts in the long run. Or we could say we expect approximately 2.2 successes out of 5 overall. So they're always doing stats for football and all kinds of different sports, and they have these weird numbers and they don't always make sense. And so that's an average of 2.2 out of 5. If we wanted to make that a percentage, we could do 2.2 out of 5, and he would have about a 44% success rate. That's another way to say it. So lots of different ways to look at this. Percentage usually makes the most sense. But with the way we state it is we call it as an expected value. And it's on page 303 if you need some more explanation. So for standard deviation, it's a little weird. The standard deviation of a random variable has this big, crazy formula. It is on your formula chart. We're not going to go through how to do this. It's similar to the standard deviation we learned back in chapter 3. But it's got the probability tied into it, the P of x. I'm not going to worry about having to do that by hand. I just want you to be able to do it in the calculator. So we're going to use the football data from a couple pages ago. We're going to use these probabilities, and I'll show you how to get the expected value and the standard deviation in the calculator. Alright, so in the calculator, it explains on page 309, you take the random variables, which in this example is 0 through 5 in L1. So you take your x variables, and you put those in L1. So if you want to make a note back in that slide, you put them in L1. So stat edit. I'm going to clear out whatever's in there. I'm going to put 0, 1, 2, 3, 4, and 5. Hit enter between each one. And then P of x goes in L2, so the probability of each one. So I'm going to put 0.3, 0.16, 0.02, 0.23, 0.14, and 0.15. Sorry about the glare. So you put the probabilities in L2. I don't know if that makes it better. Alright, so you've got the x values in L1, the probabilities in L2. From there, you're going to go to one var stats, which we've done before, stat calc one var stats. So stat calc one var stats. However, before we used to just push enter. We're not just going to do that. We're going to actually, before we push enter, and in the newer calculators it's a little bit easier, you're going to push second, and then 1 for L1, then the comma button, second, 2 for L2. See the little L2 above 2? So in the older calculators, you just do L1, comma L2. In the newer calculators, L1 is the list and L2 is the frequency. So just second 1, then second 2. It'll look a little bit different in the newer calculators. When you hit enter, it gives you X bar, which is 2.2 which is what we got previously, 2.2, that's your expected value. And then we're going to go down to sigma x to get our standard deviation. So sigma x equals 1.86. So it means the same thing, standard deviation of x. And in a minute, we'll put this on a bell curve with the mean and the standard deviation. But we're just going to use the calculator to get that number, sigma x. Notice it doesn't have s of x because we don't do samples here. We always take the entire distribution. And so you always have x bar and sigma x. You don't have to do either of those by hand. X bar is easier to do by hand, but sigma x is not. So you can get both of those. Again, stat calc, one of our stats. But before you push enter, you push second 1, comma, second 2 for L1 and L2 to make sure you get the right numbers. All right, I'm going to pause there, and then we'll start section 6.2.